This is Bill Langdon of the Crest Group UCL. I'd like to talk to you about my poster, First and Fatherless Crossover. In addition, I'll be giving a presentation at the Landscape Aware Heuristic Search Workshop, and there will be a chapter in the forthcoming book, Genetic Programming, Theory and Practice. So the idea is we want to exploit information theory to explain convergence in genetic programming, and the poster explains how we exploit that to get a massive speed up for genetic programming. So the idea in the little picture at the bottom is we have a tree, it's an inverted tree so that the root node is at the top, and that's where the answer from the tree pops out. So in this tree we have about 1,000 arithmetic operations. So they're floating point, add, subtract, times and multiply. And at each of the nodes in the tree, we take two 32-bit floating point numbers and we do something with them and we generate a 32-bit answer. So from an information theory point of view, each of our 32-bit floating point numbers has at most 32 bits of information in it. So we're taking at most 64 bits of information and generating no more than 32 bits of information. So information loss is inherent in these operations as it is in almost all computer science operations. What the picture shows is we have a large program, and in red at the bottom, we make a change. So here we're making quite a large change, and on each of the test cases, the new program makes a different answer to the original, and that's shown by the black node. So that indicates that on all of the test cases, the new and the original program produce different answers. But as we move up the tree, as we go through different levels of functions, the change that we've made in the red nodes is progressively diluted. So each of the side nodes also adds information into the process, but in the process, it dilutes the original change. So we go through blue nodes, red nodes, yellow nodes, indicating that we're progressively losing information about the change. And when we reach the top of this yellow chain, it indicates that there's no observable difference between the original program and the new one. And at that point, we can stop. Because once there is no difference on the test cases, then there'll be no difference in the output at all. So our original program and our new program produce exactly the same answers on the test cases, and therefore our new program has exactly the same fitness. So from a GP point of view, all we need to do is copy the fitness of the parent into the child. And notice the grey nodes. So the grey nodes have not been evaluated at all. So this is where the speed up comes from. And this is essentially true of programs in general, that if we make a change sufficiently deep within the program, sufficiently far away from the output, then that change is not going to be visible in most cases at the output to the program.